Um, and we're just going to talk about the latest on exoplanets. And again, like I said, that if, we'd love to find life, but the reality of it is the first step in doing that is actually going out and saying, okay, are there planets beyond Earth? Because if there are no planets beyond our solar system, then this is really kind of a dumb question. And this is where we want to start. And so if we start, I think a good place to start is to just kind of have a picture of our solar system. Because as we go and look out, this is going to provide the roadmap or the anchor or the starting point for what we go out and look. And if we look in our solar system, you have the sun, and all of the planets are drawn to scale. The distances are not, but all the planets are drawn to scale. You got the sun over, or we'll put it on the left. You go out from there, you've got Mercury, Venus, Earth, and Mars. These are the rocky planets in our solar system where, though they have an atmosphere, the dominant composition of these planets is a hard, solid object. Then you go out from that, you've got Jupiter, Saturn, Uranus, and Neptune. These are planets that are dominantly rock or gaseous or icy. If you were to, whereas you come hit the Earth, Earth, Venus, Mercury, and Mars, you hit the surface, bang, you stop. Whereas Jupiter, Saturn, Uranus, and Neptune, there's no discernible surface. You just kind of go through this deep, dense cloud bank that goes many, 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 many miles into the planet. And then, of course, you have dwarf planets. And if you want to really get into a stink, just get up somewhere and declare that Pluto is no longer a planet. You'll find a lot of people that are really upset at that. Most people that don't understand why it's not a planet, and some that understand that it's not a planet and really don't care about it. But I find it interesting. Those are some of the more if you really want to generate a discussion, you just say that Pluto isn't a planet, and you're going to get people come out of the woodwork with their voice on whether it is or isn't. But for our purposes today, Pluto is not going to play much. What we really want to concentrate on here is the order and distribution and what our solar system looks like, because that's what we're going to be going out and looking for. And so the way our solar system is formed, again, you got the sun at the center, you've got Mercury, Venus, Earth, and Mars, all of these largely on circular orbits. They're just a little bit outside of circular. They're all elliptical. Then you've got a gap. Then you've got Jupiter, Saturn, Uranus, Neptune, the four large gas giants. And this is the way people thought the vast majority of solar systems out there would look. And if we kind of now, instead of looking at it from the side, kind of get up above and take a bird's eye view, excuse me, if we start here with the inner planets, again, you got the four inner planets there, Mercury, Venus, Earth, and Mars. You got a large asteroid belt, and then you've got the orbit of Jupiter out here. And now, so if you zoom out and come here, you see the orbit of Jupiter in there. You got Saturn, Uranus, Jupiter, Saturn, Uranus, and Neptune. You show Pluto on there just for scale and to get a sense of what's going on. And one of the things you'll notice is that where all of the other planets have these nice kind of concentric orbits, Pluto's orbit is very different. And not only is it off center, it's actually very tilted compared to the rest of the solar system. So all of the planets in our solar system pretty much orbit in a plane. You've got this object Sedna, which if you zoom out there, you can see the orbit of Pluto in there, and Sedna's got this really weird orbit, elliptical orbit. And if you continue to extend out, you can, again, for scale there, you can see the orbit of Sedna. You get the Oort cloud out there. And by the time you get out to the Oort cloud, you're out at the boundary of the region where the sun is the dominant influence. You go beyond that, and you're really out in interstellar space. And so this is kind of the picture. You've got the rocky planets in the middle, in the interior, you've got the gas giants on the exterior, there's nice circular orbits, you've got these weird elliptical orbits in small stuff that's orbiting out beyond the orbits of the planets. And so that's kind of the picture of what we expected. Now, as you go out, and ask, are there planets around other stars? You really have to first ask the question, how do we find planets? And it's really quite a difficult task. And to give you a scale for how difficult the task is, I don't have a good picture of it in this one. The person who grew up in Missouri at least knows what a lightning bug is. These are these little bugs that give off, their rear ends light up, and that's cool in and of itself, because if you look at how efficient that light generation mechanism is, it's about 100% efficient. So none of that goes into heat, which is really good because you don't want to heat up the bug. That would be bad. The transmitting the light from the fluid where it is out to the air, you're going to get a lot of reflection because of the change of indices of refraction as you go from liquid to solid or to gas. We've actually looked at the scaling on that and used the scaling to actually improve the efficiencies of LEDs that we make by 50%, just by emulating what the Firefly does. So that's a whole nother study that I think is interesting. But if you take a Firefly, it has this little bit of light that right as it gets around nighttime, you can start to see it. And if you want to catch them, you have to do it at just the right time, because the light, you can see the light, but if it's too dark, you can't see the bug afterwards. And if it gets too dark, or if it's too early, or if it's too early in the evening, it's not bright enough that you can see. And so this isn't a particularly powerful light. But if you imagine now taking that Firefly that gives off that little bit of light off of its rear end, putting it on the rim of the most powerful searchlight that we have made. You think of the ones where they did it with the Twin Towers, these big beams of light shining up into the sky. Take a Firefly, put it right on the edge of that beam, and now say, build an instrument that can find the light of the Firefly in amongst the spotlight. It's a difference of about 1 in a billion, which is in optical light the kinds of, when you compare the light of a planet compared to the light of a star, it's about the same difference there. So it's enormously difficult to find planets. The cool thing about science is that scientists are pretty creative and have come up with a number of ways to go about doing this. And so I want to share and give you a little bit of outline of how they do it, because that influences what we actually know about those planets. And so one of the most prolific techniques, at least originally, it is no longer the most prolific, is what's called the radial velocity. And I've got this little diagram there where a planet doesn't actually orbit around its star. Both of those objects orbit around the center of mass. Now, the center of mass is almost always within the star, the radius of the star. But what you could imagine, or what you have going on there, is that as the planet and the star orbit around the center of the mass, the star actually wobbles back and forth. And if you're to the side of that, there are going to be times where the star is moving towards you and times where the star is moving away from you. And if you train your telescope to look at the star, you can actually detect this radial velocity through Doppler variation, and you can find planets. Now, the types of planets that you're going to find are massive planets, because the more massive the planet, the more it's going to move the star around. You're going to find planets that are eccentric or close to the star, because again, the closer the planet is to the star, the more it's going to move the star around. And those on eccentric orbits, because the more eccentric the orbit, the more variability in how the star moves. And so those are things that allow this technique to give a signal that astronomers can detect. Now, if you ask the question, what sort of planets do we find from this, or what sort of information, do you get? You get information about the mass, and you get information about the orbit of the planet, and that's really it. And it's really limits on the information, because what you don't know in most of these scenarios is, are you looking at this mostly edge on, or is it tipped? Because if you're looking at it kind of from a 45-degree angle, all you get is an upper limit on the, or a lower limit on the mass. And you get some information about the orbit. So you don't actually get a ton of information, but you get a little bit. Now, there's another technique, and I'm going to give you 4 here, just because these are the ones that have found the most planets so far, which allow us to assess where are we going and what are we going to know. This one is kind of a cool, where it's called microlensing, and really the idea here is that as light goes by a massive object, the gravity of that object will cause the light to be bent. And so for things that are far apart, it's no really big deal, but things that are massive, or where the light is passing very close to something, that light will get deflected, and it does two things. One, it gets deflected, but if the organization is right, it actually magnifies the light, so you'll be able to see things that you wouldn't normally see. And so the way this plays out is typically you monitor a bunch of stars, and occasionally one of them will line up with a planet or star that has a planetary system, and the star will give a big hump in the light intensity, and the planet will give a smaller. And so you know what size signal you're looking for depending on the planet size. And what's nice about this is that it allows you to see planets down to a few Earth masses. You can watch many stars, so you can find lots of these. The problem is you have no follow-up because it relies on a specific geometric configuration, and that typically just happens once and then never again with the particular planetary system. And again, the information you get is you get the mass and the orbit, but what is different about this than the radial velocity is that it allows you to see planets down to a few Earth masses, where with radial velocity, we're dealing really up around Jupiter, Saturn size planets. Another one, and this is kind of the holy grail of planet finding, is direct detection, where we actually find the light from the planet itself. And so the idea here is that you find some way to block out the light from the star, you mask it off, and then you hope to find the light from the planet. Now, for this, obviously, the closer the planet is to the star, the harder that's going to be. And typically, when you try and block the light out, you don't just block it all out, it bleeds out into other areas. So in this image, the light from the star is down here in the center. It's blocked out, but you can see the light's kind of bled out around it. And if you look at the scale, the distance from the Earth to the sun is this little H-looking thing next to the Earth. So even the region that's getting blocked out already includes the Earth. You go out to Jupiter, that's kind of getting right towards the edge of this fuzzy stuff. But if you get out to Neptune, now you can start seeing things. And so there's clearly two planets there. Just so you know, naming convention of planets are always, the star is the determiner. So this star is called GJ 758. It's object A in the system. The first planet is going to be object B. So GJ 758b is going to be the first planet found. C will be the second planet. D the third. That's the naming convention. And that's true of all the planets or planets outside our solar system that we have found. These also, you tend to find bright planets, and so those are younger planets, because when planets are first formed, they're hotter, they give off more infrared and violet, or infrared and visible radiation, so that's when you're going to find them, but they're going to be distant. But from this information, you get mass, or you can get mass, you can get the orbit, but you can get temperature of the planet, you can get what the atmosphere is made of. Once you've got the light, you can now do lots of things once we develop the tools to see how the light's distributed and everything. So you can get a ton of information about the actual planet. And the most versatile so far, and by far the most prolific at this point, is what's called the transit. And this, again, relies on a special geometry where the star and the planets are orbiting around the star in the same plane that we're looking at it. And then every now and again, these planets will pass in front of the star, and it will dim the light from the star. So if you're looking at the light from the star, you're going to see these dips here where it goes down. And depending on the size of the star, we have technology that actually allows us to see planets down to Earth-type masses. The key feature is geometrically they have to be aligned so that we can see the dip in the light star. It's got to be around stable stars, because if the star's really variable, it's just going to be washed out in the noise. But the information you get from this is you get the size of the planet, not the mass, but the size. You get the physical size, you get its orbit, and if things line up right, as you look down in the wings here, where the light's going down and going back up, the light from the star is passing through the atmosphere of the planet. And so if you can have tools that are able to analyze that, you can get information about the atmosphere and temperature in certain instances. We can't do this regularly, and we typically don't get very good data here, but sometimes we do. So those are the 4 different techniques that have found most of the planets. And if you now go plot all of the planets we found, and this was up to date as of about a year and a half ago. Not really a lot has changed. There's been a few more that's thrown in there, but most of these, you see that you got all of the radial velocity planets that are found up there. You got these blue or transit. That's from the Kepler telescope. And if you kind of you notice that the upper left-hand part of this plot is occupied, and so you got rotation period. Earth has a rotation period of 365 days, so that would put it right in this range here. Mass is in terms of mass of the Earth, that'd be right here. If we put our solar system on here, the planets of our solar system, what you notice is that we can't detect our solar system yet, or at least the planets in our solar system. And so need to recognize that limitation in whatever we talk about. So we can talk about, well, we found planets that look like this or that. And I think there's obviously things that we can do that weigh in on how common is our solar system, at least in terms of what we found. But you do have to recognize we can't actually find our solar system. Or if we were orbiting a different sun, we couldn't see our solar system. And so just keep that limitation in mind. So now the question is, what have we found so far? And again, I do want to go back and set this. Let's see, the first planet outside our solar system was found in 1992. So we're almost 30 years of finding planets outside our solar system. We found thousands of planets. It's 4, 5, 6,000, maybe 7,000 planets that we found. So there's a lot that we found. The expectation was, when we started, was that our solar system was typical, run-of-the-mill, and ordinary. So what have we found? Well, starting in 1992, I guess maybe it was 1990, we started finding planets, and you can see that virtually every year, I will say this plot was made in 2015, so 2015 looks small, but it looks like, as you can see there, that the number of planets is growing exponentially. And that's just really a reflection of the better technology we did allowed us to see more space, and where we found more space, we found more planets, and it just continued to grow. And that trend extended beyond 2015. I think right about the time Kepler quit, the exponential quit, but only because we quit having technology that allowed us to explore more and more space. So the more we've explored, the far more planets we found. The interesting part to me, though, is when you start asking, okay, what are the features of those planets we found? Well, if you plot them in terms of the mass of Jupiter, so here's 0. Jupiter would be right down here in the bottom. There's a lot of things much heavier than Jupiter. What you notice is that as you go higher in mass, the number of planets drops off. And again, that's exponential, because this is a logarithmic scale over here on the y-axis. So as you go to higher and higher masses, the number gets smaller and smaller, but we would expect that trend to be true going the other way. If you go to smaller and smaller masses, the number grows exponentially as well. So we can use this sort of data where we look at how many we found, what the masses are, orbits, and stuff like that, and begin to ask the questions, let's say how many Earth-like planets? Let's assume this trend goes up, and we've extended it down to about Saturn-sized planets and below, and it appears to be the case. What this means is that obviously larger planets are easier to detect, but the abundance increases as the mass decreases. And so if we extrapolate that down, just in our galaxy, there are going to be 160 billion planets Neptune size or larger. And if you go down even further, 400 billion planets Earth size or larger. That means every star in our galaxy averages more than one Earth-sized planet orbiting around it. So now when you begin to start asking the question, how many habitable planets are there? If you define habitable as in that range where liquid water could exist, there's going to be lots of planets like that, because every star is going to have an Earth-sized planet. There's going to be lots of planets in the water habitable zone. Now, before we get to discussing the implications of that, let's kind of talk about some of the planets we found, because The first planet we found actually was orbiting around a pulsar, and we found it through timing. But as we started using the radial velocity technique, that was what we first found. The first few finds were really pretty startling because Jupiter takes, I think it's 12 years to orbit around the Earth. Or sorry, it doesn't orbit around the Earth. 12 years to orbit around the sun. As they were looking, using the radial velocity technique, they were looking at stars and finding evidence of a planet that went around on the order of days, maybe months. And these had to be Jupiter-sized planets. And it was very unexpected that we found planets like that. And so we've got these massive planets that are orbiting close to the stars. So, you know, on this diagram here to the right, you know, the stars shown there on the left, those are the yellow lines. The axis there, 1 astronomical unit, that's the size of Earth's orbit. Jupiter's out at 5 astronomical units. I think it's 5.2. And you can see that, you know, of the 178 known exoplanets that they found, virtually all of them were well within Earth's orbit or down around Earth's orbit, not out where Jupiter is. And all of these have circular orbits, which tells you something about how they formed. But the problem is they could not have formed where we observed them. And I'll get to that in a second. So what that means is that it must have migrated. So now let's go back and take a picture of our solar system. You've got the sun, the 4 rocky planets, Jupiter, and all the gas giants out there. And so if like happened in our system, the gas giants form further out, and then Jupiter now migrates down to inside Earth's orbit, down around where Mercury is or even more, think what that's going to do to the rocky planets. Jupiter has more mass than any other, or you take all the other planets and add them up and they have less mass than Jupiter. It's by far the largest gravitational influence in our solar system besides the sun. As it now moves through the inner solar system, it's just going to induce chaos and eject planets and swallow them, kick them into the sun, kick them out into the distant reaches. It's going to mess up any sort of habitable planet that's already formed. But that's what has to happen, because in order to get a Jupiter, you have to form further out. And the reason why is that what allows Jupiter to form is the way planets form is stuff starts to clump and accumulate together. And as it grows large enough, it moves from stuff colliding to where it gravitationally pulls, and eventually gets large enough where it can pull gas and ice in and grow these very massive planets. But in order to do that, there's got to be a lot of ice around so that things can clump together better. And that happens out around the frost line, which in our solar system is right around 5 astronomical units. Lo and behold, we see Jupiter form just outside the frost line. All of the planets that formed outside the frost line are much larger planets, and you can explain them based on where they formed and how the density of gas and ice in our original, as the solar system was forming. And then inside that, these rocky planets, they take longer to grow. So by the time they get large enough to accumulate a bunch of gas, the sun has gotten bright enough that it's driven all that gas out. So if you want to get giant or Jupiter-type planets, they have to form further away from the star and then migrate in. And you can just imagine the chaos that's going to wreak as those planets move through the inner part of the solar system, where the rocky planets, where life can exist, are going to grow. So if we take a look now, let's take a look at this habitable zone idea. And again, the habitable zone is just the idea that if you're too close to the star, you're going to receive too much radiation and the surface of the planet will be so hot that all the water will evaporate. If you're too far away, it's going to be too cold and it will all just freeze and you won't have any sort of liquid water. And without liquid water, you're not going to get the chemistry that life requires. So here's one of those planets, the potentially habitable planets. And you can look here, it's Kepler 186. It's got a planet right inside the habitable zone. That's that green, the light green part is where we expect it. You know, it's something akin to our solar system, or similar. No, sorry, the inner habitable zone is out of, or you know, if you look at the numbers there, the inner habitable zone is about 2.4 astronomical units. The outer habitable zone is about 0.5 astronomical unit. So this is something much smaller than our solar system. a compressed version, which means it's a smaller star. There's other problems that arise with a smaller star. We can go out and look. Here's Kepler or Ross 128. Something where the planet orbits and it kind of occasionally goes inside the habitable zone. And so, people keep track of those. And then here's one that made a lot of news not too long ago. It was TRAPPIST-1. It's got 3 or 4 planets inside the water habitable zone there. 3 or 4 of these that orbit inside there. And so people were pretty excited. Again, notice the scale though. The inner habitable zone is 0.02 astronomical units. So this is very, very close. If our sun were here, this would be very, very, very close to the sun, which means all of these are going to be tidally locked and cause some other problems. But one of the things I wanted to show is, if we take a look at TRAPPIST-1e, this is the one that's kind of right on the inner part of the habitable zone here where it's most likely to be good. If you take a look at this planet, you can watch it as it goes around, and it'll go around a number of times. But the interesting feature is go up and look at the temperature as it goes around. Now, just to be there, Kelvin has the same units as Celsius. So 1 unit Kelvin is 1 unit Celsius. 273 is 0. That's where water freezes. Notice how much the temperature of the planet changes as this planet orbits around its sun. It goes as high as about 260 Kelvin and drops down to 240 Kelvin. So 20 degrees Celsius just as it orbits around its star. And it orbits around its star on the order of days. When we're talking about global warming, we're talking about 1 or 2 degrees Celsius over 100 years and this is going to cause fairly catastrophic changes here on Earth for life. So if you're having 20 degrees Celsius in the span of a day, that's going to be a big problem. So when you talk about habitable planets, there's a number of things. The reason I point that out is there's a number of things you have to pay attention to. You have to pay attention to how stable is the planet. One of the things we're not going to be able to talk about because we have no information on it is what sort of atmosphere do you have? What other sorts of planets are around? Did the gas giant migrate through there? These are all things that I think play into what make a habitable planet. And so if you go out to G, which again is listed inside that habitable zone there, again, look at the temperature. This would be considered habitable, but it's down around 200 Kelvin, which is about minus 70 Celsius. That is incredibly cold. Question, it's now you got to remember for reference, I think Earth, lacking an atmosphere, Earth should be about minus 15 Celsius. With its atmosphere, it's about 15 Celsius. So the atmosphere makes about 30 degrees worth of difference. So if you get a very, very dense atmosphere, this could conceivably bring the surface temperature of the planet up to something where liquid water could exist. But if you got a really dense atmosphere, that's also, at some point you get so dense that the atmosphere prohibits the light from getting to the surface. So there's lots of things that play in here. And one of the things that stands out is that the type of atmosphere plays a huge role in what sort of planet you have, or how the surface of the planet looks. So that kind of gives you a sense of what have we found. And the way I would characterize it is this: when you're looking for a habitable planet, you want to find a planet where life could actually be. Trying to give you a sense of how hard that is to do, given what we know. Imagine, if you will, you've got a distant light bulb, 100-watt light bulb off in the distance. You've got people that are walking past, and you're kind of watching from a mile off. It's night. You've got a telescope. You can look, and I want you to choose an NBA caliber basketball team. But all you get to see are the occasional shadows as people walk back and forth in front of the light. How reliably do you think you're going to get that basketball team? Probably not very well. You might be able to find the taller people. You might be able to find, but you're going to have no idea how fast they are. You're going to have no idea whether they can shoot. There's just so much about making a basketball team that you don't know. Well, that's kind of helps give you a picture of when we're looking for habitable planets, planets that could actually host life, what we need to know is so far beyond what we actually know. And until that changes, everything you hear about finding habitable planets, you need to take with a grain of salt. It's great, fascinating progress, but it's not really getting down to the information that we need to know. So one way I thought that I really appreciated kind of helped me get a sense of how do we take all of these things, because you can't just look at just the orbit or just the atmosphere. You know, there's a whole bunch of things that make Earth habitable. And there were, you know, you're going to have a suitable energy source. It means you got to have the right kind of star. You're going to have a solid surface with the right temperature. The planet's got to be the right temperature with certain radius. And so there was a paper published where you started saying, okay, you know, we can look at the mean radius and we can reference it to one Earth unit and then give some sort of weight based on if the radius is too big or too small. You know, you can parameterize that and figure out how close is it to being what we think would be habitable. And you could look at the density and the escape velocity. And I'm really not so interested in what are the numbers, but the idea that you can continually add numbers, add parameters to this as we learn more and more about what we can actually observe, because all of these quantities are actually observable. And now you could look at this, you could look at the, you know, this Earth similarity index, you could look at the surface, you could look at the interior, map everything out. And, you know, if Earth is up here, the closer you get to Earth, the more Earth-like it's going to be. And those are going to be planets where they're more likely to be habitable. And I love this way of looking at it because it does a couple of things. One is it actually codifies this idea that there are a lot of things that play into this. And so we can't just look at one or two parameters. We got to look at a bunch. But it also identifies planets where we could go out and explore more thoroughly to see if these things are more and more Earth-like, do they actually have life? Now, we don't have that capacity yet. But in the next couple of decades, we're going to develop more and more capacity to do that. Really, the question we want to know is not, is Earth, you know, we know Earth is here on life. We can build things that says Earth is incredibly well designed. But really, the answer to that is, are there other places where there's life? And to answer how well designed Earth is for life, or whether it's rare or not, we need to find other planets that are like Earth and then ask whether there's life on them or not. So this is a good way of finding that there are going to be lots of planets that are going to be on this spectrum of how Earth-like they are or not. When we get around to actually searching for life, it'll help us evaluate whether Earth is rare or unique or not. You know, and if you add all the Kepler planets, you know, you just kind of look there, that's that, and then you add all the Kepler planets, that's the dominant amount of them. You see, we're getting stuff that's out here very similar in interior, but not much on the surface. You know, again, to get a temperate surface, these are going to be too hot, too cold, something like that. You know, what I find interesting is this planet here, which I think is GJ581g. This planet may not even exist. It's a question whether it's an artifact of the data or whether it's truly a planet or not. But again, this allows us to assess things in a large scale, recognizing that there are a lot of factors that play into whether something's habitable, not just is it the right distance from its star. You know, and it's recognizing that scientists are recognizing we've got to look at a number of factors. One other thing that I think plays into this that I do think helps us understand how to go out and look is to look at what we find in our solar system. Because again, Venus and Mars, depending on how you define that habitable zone, they fall within that habitable zone. But we can go explore these in great detail where we can't for planets around other stars. And what we find is that Venus has an incredibly heavy atmosphere, 30, I think it's about 40 times more dense than Earth's, incredibly hot temperature. It's so hot that if you had a piece of paper on Venus, it would just spontaneously burst into flames if there was any oxygen there, which there isn't. It has no magnetic field. And so it's similar in size to the Earth. I think it's about, you know, over 80% the mass of the Earth. So it's similar to Earth. It would characterize as being habitable given the information we have, but Venus is not habitable by any stretch of the imagination. Similar, when we go look at Mars, it's much smaller. It's very cold, well below the freezing point of water. and it's got massive volcanoes on it, and the surface of Venus, or sorry, the surface of Mars, or the atmosphere on Mars is about 50 times less dense than the top of Mount Everest. Now, you put humans up at the top of Mount Everest and we're starting to die. Humans can't live up there though. Human body will just eat itself because there's not enough atmosphere. Venus or Mars is 50 times less dense atmosphere. And so what's interesting though is that we say both of these planets seem to start out with a similar composition, with an abundance of water. But yet 4.5 billion years later, neither of them have any liquid water compared to Earth. Water just covers the Earth. But as we go look at Mars, let's just say that we actually, we put 2 rovers out on Mars. They were both supposed to last about 30 days. They ended up running for 7, 8, 9, 10 years. They both had 6 wheels. One of the front wheels seized up after a number of years. NASA, being the creative souls that they are, just turned it around and drove them backwards, dragged that wheel along. And as that wheel dragged along, it unmarged some of this white stuff. Can't unearth it. It's on the wrong planet. So it unmarged this white stuff. This white stuff is actually 90+% pure silica. Now, do you know how you get 90+% pure silica? You have a large standing body of water fed by tributaries that are bringing silicates in, and then the silica, drawing a blank on what the term is for where it comes out of the water, precipitates out and settles down to the bottom. And so there's evidence that Mars had liquid water in the past. In fact, there's water ice on it. So this is Phoenix. It's a lander that had a claw on it. You can see it clawed through there, and you can see the white silica in there, on Sol Day 20. But if you notice, these 3 little rocks down here have disappeared 4 days later. Well, that's exactly what you would expect if those were actually water ice cubes instead of rocks. So there is water ice on Mars. We see evidence of, actually see evidence of snow falling. Probably not ice snow, but water snow, but nonetheless. But the thing to point out is that while Mars has evidence of having had liquid water in the past, all of it's gone. And so that raises the question, why does Earth still have its water after 4.5 billion years? Because Earth has gone through some enormous changes. The sun has gotten 30 to 40% brighter over the last 4.5 billion years. That's going to cause huge changes, huge climate changes on any planets that are orbiting around it, because the planets of the orbits of the planets don't change much once you get past about 500 million years. There are enormous geophysical changes. When Earth formed, it was covered in water. There were no there was no land. Had some volcanoes. Now we have regular land. So there's enormous changes geophysically speaking. The kinds of life have changed from single-celled organisms up to incredibly complex and incredibly diverse life. There's been enormous atmospheric changes. The original atmosphere of Earth had no oxygen in it. Probably a lot of carbon dioxide, very dense. It's been dissipated, regassed. It had a era where it's changed from no oxygen to a bunch of oxygen, which plunged it into a deep ice age that probably only changed because of all of the geophysical activity. And ultimately, humans have arrived and caused these changes. And yet, in spite of all of these incredible changes, we have record that the surface temperature of the Earth over the last 4 billion years has not changed outside of a 20 degrees Celsius window. And so we see this incredible coordination between these enormously powerful processes, but yet they all work together to maintain this habitable environment over the last 4 billion years. That's pretty remarkable. And that, really the question is, has that happened anywhere else? Well, we can't measure anything except for some of the astronomical changes on these planets, but this is really the information we want to know. So, are we close to finding life out there? No, not really. We don't even have the information to do that. But what if, just on the off chance we get lucky and happen to find life out there? What do we do with that? Well, the way I would say it is this: we're probably 2 decades, if not more, away from having the technology that allows us to actually go out and say, okay, is there life on that planet? Where we have the tools to explore the atmosphere, figure out whether there's actually water on the surface of the planet or not, to do any of that. So we've got a long time before we can answer the question, is there life out there? But we can think about what is there life out there right now, and especially from a Christian standpoint. And what I find interesting is that this is not something that a few hundred years ago, Christian, or even in the last 40 years, Christians have said, wait a second, we might find life out there. What are we going to do with it? Christians have been thinking about this for millennia. You can actually find people writing about it. Christians, Galileo and Kepler, both had a different view on this. Galileo thought Earth was designed and Earth was the only place that had life. Kepler thought that life was scattered throughout the cosmos. Both of these devout Christians trying to seek and understand what God had done in our universe. I kind of jokingly, it wouldn't surprise me if we had a record of what Adam and Eve talked about, that Adam and Eve were talking about this in the Garden of Eden. This is just one of those topics that's that fascinating. But what if we find life? And this is something I got to say that's a little bit uncomfortable to me to think about, but it's very encouraging to think that Christians have thought about this for millennia and have thought, even if we find sentient life, that really doesn't require Christianity, that would readily fit within historic Orthodox Christian thought. Because it may be, let's just look specifically at redemption. And there's a huge discussion you could have about this. But, if we find that, it may well be that Jesus' work here brings redemption for all sentient extraterrestrial life. That may be the mechanism that God has done. I mean, I had thought this for a while when I was first in college. This was kind of my first solution, so these other life out on other planets, their scriptures are going to say, well, Jesus went, lived on earth, lived a sinless life, died on the cross, and that pays for everything. Now, that's possible. It could be that Jesus incarnate on each type or on each planet, because we know that humans are made in God's image, but we don't fully reflect his image. So maybe there's a human image, but there's also a Klingon image. And so Jesus takes on a Klingon nature and dies. So that's a possibility. We wrestle with that. Well, why is Jesus dying everywhere? Well, why did he die in the first place? Because God loves his creation, the beings he created. Maybe God has another means of redemption. Could be that no redemption is possible. That seems to be what's true for the angelic realms. Or it could be that no redemption is necessary because those creatures never fell. That topic is actually explored in C.S. Lewis's The Space Trilogy. So this is not something that Christians are actually playing catch up about. Christians have thought about this long before we had any opportunity to explore it scientifically. So just to kind of give a future, and again, a little bit of scale as we're looking at what have we found. If we look, there's the sun, there's that little circle around it. These are the planets to date that lie within about 300 light years from our sun where we can actually find exoplanets. When you consider how large our galaxy is, we surveyed a pretty small fraction of it. So I'll give you some take-home thoughts. Before I close, I'm going to open it up for some questions here. But really, I just think this is a fascinating time to be alive. Our floodgates are open. We're finding planets. There's a lot of stuff that's coming out here. We're going to find that Earth-sized planets in the water habitable zone are going to be common. I can point to you scientific papers that say roughly 20% of stars have an Earth-sized planet inside the water habitable zone. But really the question is, are they habitable?